Hi everyone, welcome back. This is Earth and Space Science 101, and this is our third lecture of the unit on plate tectonics. Today we're going to be talking about earthquakes. So this is going to be a direct segue from our last lecture where we were talking about geologic structures. The vast majority of earthquake activity happens along faults, and most faults occur along plate boundaries. So you can begin to see how all of these subjects are going to be interrelated. All of them are important in understanding the Earth and understanding the plate tectonic cycle. From this lecture, we're going to go on next time to talk about the Earth's interior. And our main sort of concern, our main utility of earthquakes is going to be in allowing them to tell us about the Earth's interior. So we'll get into that in a little bit. But for now, I wanted to start by giving you a definition for the word earthquake. It's maybe not something that would be entirely necessary if this class were being taught in Southern California or Italy or someplace where you actually have earthquakes, but we are in a particularly earthquake-less region. We don't have a whole lot of tectonic activity to speak of in general here in Louisiana, much less high magnitude earthquakes. So an earthquake is simply just a trembling of the land surface and of the subsurface generated because of movement along a fault or some other activity that might create that same effect. So other things that can potentially create earthquake activity might be any kind of volcanic activity, magma moving underground underneath maybe something like a somewhat dormant volcano. Anything like that can also sometimes release waves, seismic waves, and create an earthquake. But like I said, most of them are going to occur because of motion along a fault. So the idea behind this is that rocks can store a certain amount of strain. So as we learned last time, geologic stresses, compressive stresses that squeeze, tensional stresses that pull, and shear stresses that create that sliding motion, those stresses are going to be because of plate tectonics. Tectonics is going to create those stresses, and then that progressive strain can then build up in rocks. So you can essentially sort of squeeze and squeeze and squeeze on rocks, or pull and pull and pull on the rocks for a certain period of time before the rock will actually rupture. And what happens as a result after that is that there is a break in the rock and that there is displacement along that break. So essentially a fault is created. Or if it's not the creation of a new fault, you might have some displacement along a pre-existing fault. But you have to build up a certain amount of strain first. So this could represent hundreds possibly or even thousands of years of progressively stored strain that's released all at once as movement along a fault. Now, this theory behind earthquake activity being one, as a result of fault motion, and two, because of progressively stored strain, this theory is called the elastic rebound theory. So the idea here is that rocks behave elastically up to a point, that they can essentially have a little bit of give in them. They can store that strain until the rock ruptures and brittle deformation takes place, i.e. a fault occurs. So this fault, the point of initial breakage along the fault, is typically not going to happen at the Earth's surface. So it would be very, very weird, very strange for the actual focus or the origin of the earthquake itself to be at the Earth's surface. Typically, it's going to be deep, deep underground, maybe only feet underground, but more often miles underground. So there's still a lot of the Earth's crust, a large thickness of the crust that will act brittly even when you start to go deeper and deeper and deeper underground. It's going to be very, very deep in the crust before you get ductile deformation taking place and things like folds occurring instead of faults. So we refer to the point of origin of the earthquake and the origin of the seismic waves. These are going to be waves generated by an earthquake that we see and feel as a movement of the ground surface. The focus is going to be the origin of those waves, the actual point of origin underneath the surface. Now, that's probably not the word that you're used to hearing when referring to the origin of an earthquake or the place where an earthquake occurs. The much more common term that you hear used for that is the epicenter. But the epicenter is simply just the point above the focus of the earthquake. It's the surface expression of that point where the earthquake is happening. So from here, we're going to start talking a little bit about the actual seismic waves themselves. Now, we just simply basically think about it as the Earth itself rumbling, right? The Earth itself vibrating or moving, sometimes with the effect of actually damaging buildings and infrastructure and harming lives. This vibration really takes the form of several different seismic waves. Now, some of these waves, 2 of them, are types of body waves. And this just means that these are waves that travel through the interior of the Earth. These are not typically waves that are going to travel along the surface of the Earth. These are going to be the faster moving waves in an earthquake, or really anything else that's going to produce these types of waves, be it volcanic activity or like a nuclear explosion, something like that. Anything that's going to cause that vibration in the ground surface. The surface waves are going to move a little bit slower, but they're going to be originating at the epicenter. They're going to be moving or almost sort of flowing away from the epicenter in all different directions along the surface of the Earth. And most of the actual damage in an earthquake is going to be as a result of the surface wave activity and not the body waves. Now, what we're really concerned about with understanding earthquakes from our point of view in South Louisiana, viewing this in terms of the scientific application, is using these earthquakes to study the Earth's interior. If we understand these seismic waves, the body waves and the surface waves, and we understand how they work in the Earth's interior, what happens when they interact with some type of boundary between different types of rocks in the Earth's interior, then we can begin to start to understand some of the makeup of the Earth's interior without actually having to go there. It's like we can basically use these types of waves sort of like X-rays and understanding the interior of the human body without cutting it open. We can understand the Earth's interior without drilling into it directly. And this is a really powerful tool. So we're going to explore that idea a little bit more in the next lecture. Lecture 4 is all about the Earth's interior, and these seismic waves are going to be a big they're going to play a big starring role in that lecture. So for now, just remember, we have seismic waves. They have 2 different types. Body waves, they originate from the focus, they travel through the Earth's interior, and then we have surface waves. They originate at the surface, at the epicenter, and then they travel outwards. The body waves take 2 different forms. They take the form of a P wave and an S wave. The P wave, or primary wave, is going to be the fastest moving wave, and it is going to be a compressional wave, meaning that as this wave moves forward, as it moves, like let's say towards you, towards where you're sitting right now, that wave is going to be traveling in that direction, and it's going to be compressing and dilating the material it's traveling through as it moves forward. The secondary wave, or S wave, is going to vibrate in the opposite direction that it's traveling. So if the wave is actually traveling towards you, the direction that the wave is moving is forward from me, but that direction of vibration is actually up and down. So it's a sense of sort of shearing motion, and that limits the S waves in what kinds of material they can travel through. The S waves are limited to only being able to travel through solids, because the S waves basically disappear if they're trying to travel through anything in a liquid state or a gaseous state. So S waves can't travel through the atmosphere, they can't travel through water, they can't travel through the oceans, or any points of having magma in the Earth's mantle or in the Earth's core. Now, P waves, those faster moving primary waves, the ones that are compressional, they compress and dilate the material as they're moving forward, these go by another name when they're traveling through a gas. In fact, you're actually picking up on some of the P waves that I'm creating right now, simply by being able to hear my voice. A P wave is basically just a sound wave. And the speed of sound is very, very slow compared to the speed in which these P waves move through the Earth's interior and through anything in a solid state. They travel at something like 1/10 of the speed when they're traveling through air. So, by talking, by activating my vocal cords, making noises and forming words and all that kind of good stuff, I'm creating these P waves that are traveling to you so that you can receive them and process them as information. And the way that those waves work is by, again, compressing and dilating the material that they're moving through. So in this case, it's the air that they're traveling through. So I have a brief demonstration to show you regarding these PNS waves to try to kind of make a little bit more sense. I find that the easiest way to conceptualize what happens with a P wave is by using a slinky, because there's space in between each one of these little rings of the slinky. So you can already see there's a little bit of vibration here. There's a little bit of moving back and forth. But I'm going to try to get it as still as possible first. And then I'm going to just create a little bit of a sense of motion here, starting at my right hand. So that's going to be your left, and moving over to my left hand, your right. And what I'm going to be doing here, if I can ever get it to go completely still as possible, is I'm going to create a P wave. So what I did right there is activated the slinky on the one side, pulled it back and let it go, and you saw this little bit of a vibration of each one of those rings of the slinky moving forward. And then when it moves forward, it moves back again. So that's compression and dilation. The space between each one of those lines is decreasing and then increasing. So that's what happens with P waves as they move forward. S waves, again, are completely different. It would be like each one of these little lines of the slinky is actually moving, up and down. So that's kind of hard to express with the slinky. On the image that's accompanying all of this material, you can see that they use a rope instead of something like a slinky to show you what's going on with the S waves. The rope is actually going up and down, but the wave is propagating or moving from one side to the other. So that's P and S waves. P and S waves are going to be very, very crucial in understanding the Earth's interior. Surface waves are also very important to understand, but because they're going to be doing the significant amount of damage in an actual earthquake. The surface waves are very slow in comparison to the P and the S waves. But once they do arrive at a particular location, so let's say an earthquake's happening about a mile away from us, that earthquake happens, the seismic waves are created, they move out in all directions, and then they eventually come this way. Once that surface wave arrives, it takes two different forms that occur right at the same time and creates a lot of upheaval and a lot of chaos at the surface of the Earth itself. The first form that the surface wave can take is something that's called a love wave. It's named after the geologist who first began to understand what these waves are actually doing. So as the wave is actually moving through, you have a side-to-side motion of the ground surface itself. And as that motion is occurring, the wave is traveling through. So really, sort of any motion of the ground surface is bad when you're talking about infrastructure, building safety, roads, power lines, and the effect on people, of course. All of that is going to be potentially catastrophic because none of this is really ideally built for a moving ground surface. In places where earthquake activity is more common, of course, you've got codes about how strong things like buildings have to be to withstand some of this earthquake activity, but none of it is obviously ideal. So the love wave takes this side-to-side motion. There is a second surface wave called the Rayleigh wave, and that is a rolling wave along the ground surface. Now, only in a truly very, very catastrophic earthquake, let's say maybe something like a magnitude 9 on the Richter scale, would you be able to actually see the rolling of the ground surface. This is more something that's fairly minor in being actually able to visualize what's going on, but the ground surface does actually move up and then move back down again. So there's a rolling wave that's traveling along the ground surface. And this one's particularly damaging to any kind of infrastructure and the people that might be in this building underneath these power lines and influenced by this event at all. So important to remember again that these are both surface waves. They're both doing the majority of the damage in an earthquake. In actually using these earthquakes to study the Earth's interior, we don't typically use these quite as much because, again, they're not really telling us anything about the Earth's interior if they're not traveling through the Earth's interior. And these surface waves are traveling not in the Earth, but along the Earth itself, along the surface of the Earth. So they're basically sort of riding this boundary between the solid Earth below and the gaseous atmosphere above. So that's what kind of keeps them on that line, moving along the surface. So we have several ways of measuring these earthquake events. We use something called a seismogram in order to understand these waves and sort of process this information, pick up on this information, and to be able to determine things like where the earthquake happened, the severity of the earthquake, the magnitude of the earthquake, which is one way of analyzing its severity. So all of this kind of information mainly comes through seismograms. What I have for you is an image of sort of an old-fashioned seismogram, something that might have been used at the beginning to middle of the 20th century. The basic idea of a seismogram is it has to be able to move with a motion of the ground surface. So in these images, you have some kind of weighted material, some kind of block or a brick or some kind of maybe heavy material that's suspended on a spring. And then attached to this heavy material, you have essentially just something like a pin. And with any upheaval of the ground surface, with any motion of the ground surface, the spring, the weight would move on the spring, and thus the pin would move. So if you had no earthquake activity, you would basically be drawing a solid, thin line on a piece of paper. With earthquake activity, you would have a little bit of an upset of that line. You would actually have some motion of that line as the weighted material drops down and then springs back up. So when we do this, when we actually record this information, we get different types of waves arriving in sequence from a single event, from a single earthquake. We get the P and then the S wave, and then a much, much bigger arrival of the combined surface waves. Both the Rayleigh and the Love waves arrive at once. And they always occur in that order. The P or primary wave is always first, then the secondary wave, and then the combined surface wave. Now, so this picture that I showed you was of sort of an old kind of fashioned idea, an old-fashioned seismogram. What we have today is basically any machine that has a gyroscope to it, any device like a tablet or even something like a phone that can basically sort of sense where it is in space in any particular axis and any orientation. Any device like that could pick up on these same seismic recordings. They basically can just pick up on any vibration like this. So what I would invite you to do is get on a phone, get on a tablet, anything that has a gyroscope, and most smartphones would have something like this. And you can download, usually for free, a seismogram, and you can put it on the desk next to you, and you can tap on that desk, and it'll pick up on these waves. On this device in front of me, I actually have a seismogram downloaded onto it, and I can basically do the same thing on this device. So I could maybe just tap ever so slightly on the device itself or on the table next to it, like rat-tat-tat, and I would be able to pick up on those vibrations as they're coming in and being recorded by the material, and it would be expressed as those little lines. So it's pretty cool. It's kind of, it takes all the mystery out of it. All you're really doing here is just recording these vibrations. With a real earthquake, with something that's actually producing a substantial amount of seismic activity, you would have, again, the three different arrivals of the waves: the P, then the S, and then the combined surface waves. So let's look at how this actually translates into real information about the earthquake itself. If you have an earthquake happening somewhere relatively close, and relatively could still be pretty far away, it could be 20 miles, it could be 100 miles, it all depends on the sensitivity of the equipment that you're working with. You may be able to pick up on an earthquake, especially one with a high magnitude. So as that earthquake happens, all of these seismic waves are being produced, and they're stemming outwards away from the focus and away from the epicenter, again, out in all directions. So if you're located, let's say maybe 20 miles away from this event, and you have a seismogram, you'll pick up on this arrival of these different types of waves. First the P wave, then the S wave, and then the combined surface waves. Now, just one place where this recording is taking place is not going to be enough in order to actually give you a locational information, because what we can do is we can take the arrival time of the P wave and the arrival time of the S wave and use that information, the separation in time between those two arrivals, to translate into a distance away from our location where this earthquake took place. So we might be able to come up with the information that, yes, this earthquake happened 20 miles away. But we wouldn't actually know in what direction 20 miles away this earthquake happened. We don't know if it's 20 miles west or north or east. All we know is that it's 20 miles away from our location. We have a radius away from us where that earthquake happened. So it actually takes not one, not two, but at least three, and ideally more than three seismic recording stations to pinpoint the exact location of an earthquake. So you need three because when you have three circles, they will intersect at a single one point. If you have, of course, more circles, more radii around these seismic recording stations, you have a greater certainty about that one point. You have a more definite idea of where that earthquake actually took place. So that's the first major piece of information that you can determine about the earthquakes from this material directly. The other one that's also very important is the magnitude of the earthquake. It's one way that we can determine the severity of the earthquake. So the next thing I'm going to talk about is different ways of being able to process this information and determine how severe an earthquake was. But the first way that I want to go into about how you determine how severe the earthquake was is actually not using the seismic recordings at all. It's a bit of an old-fashioned way of determining what's going on with an earthquake. It's called the Mercalli scale. The Mercalli scale is not a data-driven scale in determining the severity of an earthquake. It's based on more just sources from individual people. So when I say it's not data-driven, I mean that you're working from reports from people about how severe the earthquake was, and not from something potentially less biased, like the seismic recording itself. So the Mercalli scale is a scale that goes from 1 to 12. It's usually expressed in Roman numerals. And 1 would be a very, very low intensity earthquake that most likely no one would actually be able to feel, to a 12, which would be apocalyptic. So what you've got on the scale is various points along the scale where you might have typical things that would happen. Maybe somebody would be able to see a vibration in the dishes. Maybe you would have broken windows, that kind of thing. And then you would be able to rank the earthquake in terms of the damage that it caused. So the important things to take away from the Mercalli scale is its intensity. It's based on damage. It is not based on the amplitude of the seismic waves. It's not based on the seismic recording at all. The much more common way of reporting earthquake activity, in the case that you actually have this data, is using something called the Richter scale. A Richter magnitude is a magnitude that's determined from the seismic recording itself. So we don't typically actually use the P waves in order to do this. We use the somewhat slower but higher amplitude S waves. The amplitude is basically just the height of the wiggle away from that central line on a seismic recording. So if it's a higher amplitude earthquake, you basically have a higher deviation away from that line, and you can use the height of that deviation in order to determine that is the measurement of the amplitude, maybe measured in something like millimeters, and then you would translate that into a magnitude. You would also have to have, in this case, an understanding about how far away the earthquake occurred. You'd need to know the distance to the epicenter of the earthquake. So the other thing that's really important and very, very often forgotten about the Richter scale is that it's not a perfectly linear scale. So in a linear scale, if you had an earthquake that measured at a 6 and an earthquake that's measured at a 7, that would mean that the earthquake that's measured at a 7 would basically just be maybe one little step worse than a 6. This is a logarithmic scale, which basically just means that if you had the difference between a 6 and a 7, the 7 would be 10 times as bad as a 6. And 8 would be 10 times as bad as a 7, or 100 times worse than a 6. So you can see how as you go each step higher in Richter magnitude, it's increasingly less likely that you would have an earthquake of that severity, and you get to this point of having it be increasingly unlikely and extremely catastrophic. So when you're talking about an earthquake with a magnitude of 9, these earthquakes typically happen very, very deep in the crust. So the surface expression of those earthquakes isn't as catastrophic as you would probably think, seeing as how it's 100 times worse than a 7. But that earthquake was creating a substantially more powerful event than an earthquake with a Richter magnitude of 6. So I have a little visual to kind of accompany this that gives you an idea of the decrease in instances of these earthquakes with these higher magnitudes and a correlation to the amount of energy that's actually released by the event. So when we're trying to compare something like a large nuclear test to a really severe earthquake. It doesn't really take something more than, like, let's say, a magnitude 8.5 on the Richter scale to compare to a nuclear explosion in terms of the amount of energy that's actually released from the event. So there's a reason why the Richter scale is one that you've probably heard before, and it's far more often used than the Mercalli scale, being based on real data. And typically, as time progresses, this data is more and more and more available and more common. We can get a real idea of exactly how bad the earthquake was. So when we do this, when we analyze these earthquakes and look at where their epicenter is and what the magnitude of that earthquake was, we can begin to map the locations of where these earthquakes have occurred. And as it turns out, most of these earthquakes happen exactly where you would expect them to happen, based on everything that we've talked about in these lectures so far. Earthquakes are far, far more common and more likely to happen in the future along places where we have plate boundaries. Now, in the U.S. specifically, this is going to be on the West Coast. Definitely in places like Southern California, down the coast of California, into the Baja, places where you have active plate tectonics and really fast-moving plate boundaries. That's going to be where you have far more common earthquakes. It's definitely not impossible to have an earthquake that's not on a plate boundary. It's just going to be less likely. And even when you zone in and look at these other pockets where you typically have a little bit more earthquake activity than elsewhere, those little pockets are going to have some sort of plate tectonic source. So a really good example of this is, again, in the U.S., obviously, the West Coast is going to be far more active than anywhere else in the United States. But if you're looking at these maps, you might pick up on a location where you have slightly more earthquakes than the rest of eastern United States and the eastern North American continent. And that's in the areas around western Kentucky, western Tennessee, southern Illinois, in this area known as the New Madrid Fault Zone. So the New Madrid Fault Zone is not on an active plate boundary, but we think that this marks the location where the United States, where the North American continent, began many millions of years ago to start to rift apart, much like Pangaea rifted apart 250 million years ago. The difference here is that while the North American continent began to start to split apart for whatever reason, maybe inadequate temperatures in the mantle underneath this failed rift, this point where the continent began to rift apart stopped rifting. But you still have some sort of underlying geologic tensions there. You have a little bit of this activity progressing even to this point today. So you have tectonic activity that's not actually related to an active plate boundary, but a failed plate boundary in the past, in the case of the New Madrid Fault Zone. So, like I said, worldwide, even beyond North America, beyond the United States, and worldwide, the vast majority of earthquakes are happening along plate boundaries. And we can tie in the types and depths of these earthquakes to the types of boundaries that they occur along. So as you can see on this map, we've color-coded the earthquakes that have occurred into the deep earthquakes, the intermediate depth earthquakes, and the shallow earthquakes. The shallow earthquakes are all in blue, the intermediate is in yellow, and then the deepest of the earthquakes are all in red. So as you look along the areas along the rim of the Pacific Ocean, it's called the Ring of Fire for a reason. It's where you have a lot of volcanic activity too. You basically have the destruction of different parts of the Pacific Plate and other adjacent oceanic plates as they move up underneath all of these land masses, and that's what's creating all of that volcanic activity and earthquakes. So as you look along the Ring of Fire, if you look on, say, the west coast of South America, you see lots of red, and red is all deep earthquakes. Some of the highest magnitude earthquakes in the world and in history, and human recorded history, have all happened along this area, along the west coast of South America. And there's a reason for this. You have a very, very deep subduction going on. So where all of this oceanic crust is subducting under the continent, and then doing so at a significantly high angle. So all of that creates geologic stress. That geologic stress is expressed as motion along faults, and all of this happens deep, deep underground. So these might be high magnitude earthquakes, but in a lot of cases, they're happening so deep underground, they don't create the kind of catastrophic loss of life that maybe a more shallow but lower Richter magnitude earthquake might be capable of. The places where you're going to see the most blue on this map, the sort of light blue color indicating the shallow earthquakes, is along mid-ocean ridges and transform plate boundaries. So that's where you're going to have the most geologic stress, creating the most faults closer to the ground surface on the ocean floor, and in some cases on the continent as well. So in my perspective, those are in some cases going to be the more dangerous faults to be living along because they're shallow, because you might end up being closer in location to the origin of all of these seismic waves. So the effect that they might have on you personally would be greater. So one possible side effect of an earthquake is, of course, a tsunami. Particularly if you're living in a very shallow an area adjacent to a large body of water that's not at a high elevation. So these tsunamis occur primarily, not exclusively, but primarily because of motion along a fault. Every once in a while, you could have something like a collapsed glacier, a whole lot of ice falling into the water all at once that might create a large wave, but typically not a large enough wave to what we would be calling a tsunami, not an event that would cause catastrophic loss of life and create a worldwide event. So what happens in an earthquake that causes a tsunami is that all of this geological activity and all this motion along the fault is occurring on the ocean floor. And that's when you've got the kind of circumstances where you very well might possibly create a tsunami. You have this very, very sudden motion along the ocean floor. And now it seems sudden, but it's important to remember that this could be 1,000 years in the making. This could be hundreds, possibly even thousands of years of progressively stored strain that's released all at once. So you might have, in some cases, a lot of motion along a fault. You might have something like 6 meters. That would be the same as saying something close to 20 feet of displacement along a fault. And then all of this water in the ocean that's been displaced because of this motion along the sea floor, all that water has to go somewhere. What often happens first is that the coastline appears to recede back into the ocean. The water level actually drops down for a short period of time to then be replaced with a wall of water, potentially even hundreds of feet higher than normal ocean waves, that would then just completely inundate these coastal areas. Now, what this probably brings to mind is the case that happened on the day after Christmas. It's often called Boxing Day in other places of the world, like in the UK. This happened on December 26, 2004, in the Indian Ocean, and this is commonly thought of as the Indian Ocean tsunami. In this case, what happened was you had this sudden displacement of the fault, like what I was talking about, on the seafloor with this accompanying huge displacement in the water on the ocean floor. So again, in this case, this was something like 20, 25 feet of displacement along the fault. And then all of this water then has to be in motion. It has to find somewhere to go. It gets displaced. And it eventually is going to correlate to a huge tsunami in all of these coastal areas surrounding the Indian Ocean. Some of the hardest hit areas were Thailand, Sri Lanka, and the eastern coast of India. So in order to kind of give you a little bit of a better sense of what happened during the tsunami and what happened during the resultant earthquakes, we're going to cut to a little documentary on this particular event.
The Indian Ocean, bordered by Asia, Africa, and Australia. In December 2004, millions are enjoying the holiday season along its shores, including Steve Gill, his wife Heather, and stepdaughter Charlotte, who are on vacation in Thailand.
We had arranged to go out for a traditional Christmas meal. Everything was new and warm and fairly unspoiled, undeveloped, very, very quiet. Idyllic, I guess you'd say, yeah.
In the Indonesian town of Banda Aceh, local resident Eddie Quenslow is visiting friends and family.
I went to the town, sleep in my friend's house. There is close between my sister's house and my friend's house.
At about 8 a.m. local time on December 26, 2004, everything changed. Just offshore from here, where the Indo-Australian plate subducts underneath the Eurasian plate, more than 1,000 years of tectonic stress were released in a matter of seconds.
The earthquake has a magnitude of 9.1, the third largest ever recorded. As the Eurasian plate thrusts upwards by 20 meters, it displaces billions of tons of water.
The resulting wave traveled east towards Thailand and Indonesia and west towards India and Sri Lanka. And in the tsunami's path were millions of people.
Peaking at 800 kilometers an hour, the tsunami will take 30 minutes to hit the Sumatran coast. Around an hour later, it will reach Thailand. Although they felt the earthquake, with no tsunami warning systems in place, people around the Indian Ocean coastline are oblivious to the approaching threat.
I saw the building is destroyed, and we are scared, of course, but we didn't know it's happened.
For the holidaymakers in Thailand, the first hint of the impending disaster is the strange sight of the ocean disappearing.
The bay was empty. All I could see was rocks, all the way over to the yacht club, all the way over to the other island. There's nothing there.
One of the more enduring and dramatic images of the 2004 tsunami was the withdrawal of the water level from the shoreline, leaving the entire foreshore area exposed. This is a phenomenon known as drawdown, and it's caused by the tectonic displacements offshore. While one section of the plate is thrust upwards, the section of the plate closer to the coastline actually subsides, and the water rushing in to fill that void is what causes the withdrawal of the shoreline. Had more people realized that this was the sign of an impending tsunami, perhaps more lives would have been saved.
This is the time people should have started running. But instead, the curious sight lures people onto the beach.
It was bizarre, but it was fascinating. I think I did actually briefly go to the front of the house again and look and think about, walking out. And I thought, no, that's just not right. It's wrong. Exactly how it's wrong, I don't know, but it's wrong.
By the time many react, it's too late.
Myself, my wife, and my stepdaughter discussed our next move, and we just didn't get to make it, basically.
At 8:15 a.m., the tsunami hits northern Sumatra. The city of Banda Aceh, home to over 250,000 people, is about to suffer its full force.
I'm here in the busy city center of Banda Aceh, and it was here on this street corner where some of the most graphic video footage of the tsunami was recorded. On the street behind me, the tsunami surge came flowing up the road, channeled between the buildings. Watching the footage, we see that the leading edge of the tsunami was actually slow enough that people could escape simply by running or walking. However, this part of Banda Aceh is very far from the ocean, and people simply didn't know what to do. As the flood depth increases, so too does the speed of the flow, until there's no way to escape unless you can get to high ground. That's what the person who shot this video did. He climbed up over here. And he lived. However, thousands of other people that day could not get to high ground, and they ended up dying in the waves.
Crammed with billions of tons of debris, the wave is an unstoppable battering ram. Eddie Quenslow is one of the many that scrambled to safety near the Grand Mosque.
Materials come like the iron, the stone, the rocks, the bed, shirt, motorcycle, a car. You can see people mixed with the water, everything material.
The tsunami wave came right through here. These are very sturdy concrete buildings, and many of them weren't knocked over by the tsunami, but rather the water flowed through them, between them, and actually channelized the flow and made it speed up and get deeper in some areas. The water here didn't go past the first story. It was all pretty much less than about 8 or 10 feet deep. So in terms of escaping, a lot of people could have gotten away just by getting up to the second story, as the cameraman did at the corner.
I was thinking I will die, and I saw many people need help, but I could not help because too many people need help. I saw many babies. Of course they need help. Sometimes I just put on the top because I don't know where I have to bring them, how I can bring them to where, because all is a flood. That means everywhere is water.
30 minutes after the tsunami hits Banda Aceh, it smashes into the Thai island of Phuket.
Get inside, get inside.
Steve Gill's beach bungalow is directly in its path.
I think our conversation ended when we heard the roar of the water. We still couldn't see the wave until we turned to look at the small alleyway between the two buildings. It was traveling at a speed estimated between 200 and 300 miles an hour. And it was just, the scene was obliterated by water. It was 30 foot high. And by that time, there was nothing we could do, nothing. I remember being struck by the water. Realistically, there wasn't any expectation of ever coming out the other side. It was just, is this the way it ends? Because the sheer power of what has hit you doesn't allow any space for an escape plan. There are no plans for the future. I was found in the stagnant wreckage, if you like, about a quarter of a mile up the road.
Although he soon reunites with his stepdaughter, Steve is never to see his wife alive again. Over the next 20 minutes, 3 massive waves, up to 10 meters high, crash into the small resort. 1,000 tons of water smashing down on each meter of coastline. Beach after beach, wave after wave, the tsunami brings death and destruction. In Thailand, over 5,000 people perish, with another 3,000 missing. In Indonesia, the tsunami obliterates Banda Aceh.
I could not imagine why like this I lose my best friend. I was thinking like, why God didn't take me? Better He take me than my best friend. And also, but my auntie also, we didn't find his bodies. My cousin, my cousin passed away. We cannot find bodies.
In total, the waves strike 14 countries around the Indian Ocean, taking lives as far away as Africa. The final death toll will make the 2004 tsunami the most lethal ever seen.
So that gives you a little bit of a better idea of what happens during a tsunami, how terrible it must have been for the people who lived and potentially died through that event. So not every earthquake obviously produces a tsunami. This has to be an earthquake that's taking place. It has to be motion of a fault that's taking place on the ocean floor itself. But even earthquakes that happen underneath continental crust can create a significant amount of damage, especially if you don't have the infrastructure and the building codes present in that location to be able to withstand these kind of severe seismic waves. So in 2010, on January 12th, there was a severe earthquake in Haiti. The magnitude of this was a 7 on the Richter scale. And there are certainly other places in the world that could be capable of withstanding a magnitude 7 earthquake without any kind of catastrophic damage resulting. But what happened in this particular case was this is a magnitude 7 earthquake that was happening at a very, very shallow depth. It also happened that the epicenter was located very, very close to the capital city of Haiti, and that's Port-au-Prince. So you have a lot of people living there. You have a very shallow earthquake. You have the epicenter of that earthquake located very, very close to this capital city. And possibly the worst point is you have building codes that were really not up to being able to withstand the seismic waves during this event. So entire buildings, multi-story buildings, flattened out like pancake. So it was particularly catastrophic. And this particular earthquake led to a very, very heavy loss of life, a lot of casualties as the result of this particular earthquake. Now, in Haiti, you have to not only be able to build to withstand things like earthquakes, but just like we are here in South Louisiana, you also have to be able to build to withstand hurricane damage. And that's not an easy thing to be able to mix, is to be able to build things that are capable of having a little bit of motion, and that's the case in earthquakes. Buildings really need to be able to withstand a little bit of motion, whereas to withstand hurricane winds, you need something that's going to be very, very rigid and incapable of motion. So that's sort of part of the story of what happened during this particular earthquake event. The most recent of some of these catastrophic earthquakes that you may remember happened on March 11th, 2011, and this happened off the coast of Japan. So there was a resulting tsunami in this case, plus there was actual damage just strictly from the earthquake itself. And the reason why you might remember this particular earthquake was because of the damage done to a nuclear facility in the area. Fukushima Daiichi, a nuclear plant, was inundated with water. So you had a lot of damage, both monetary damage and loss of life resulting from the damage done to that facility. So the thing that I wanted to kind of take us out on with all of this talk of all of these casualties and all of this earthquake activity in other places of the world was to give you a little bit of a sense of an idea of what it's like here in South Louisiana. And since we live here, and in some cases, some of you may have spent your whole lives in South Louisiana, you probably know we don't get a lot of earthquakes. A lot of people would say we don't get any earthquakes here. We do actually get some earthquakes, just extremely low magnitude earthquakes. So it might be surprising to hear this, but it's not uncommon. It might be something that we experience once a month, maybe a few times a year, to get even something like a magnitude 3 or 4 on the Richter scale. But especially because that scale is logarithmic, these earthquakes wouldn't be something that we would actually be able to feel at all. You can pick these up on a seismic recording station, which is why we know that they happen. But we don't really feel them. They don't affect our everyday lives. The reason why these earthquakes occur is because we do actually have faults in South Louisiana. They just aren't really driven by any kind of tectonic activity. In this case, these faults occur because of sediment loading on the coastline. Think about something like the Mississippi River. As it flows out to the coastline, it dumps sediment, it deposits sediment along the coastline, and extends itself out into the ocean. So as that sediment compresses and packs down the weight of the underlying sediment, we have these faults in place. They're called listric faults. These are shovel-shaped normal faults that allow for this compaction to occur. And whenever you have some of the sediments sink down or sort of settle down along these faults, kind of just slump down, we call this subsidence of the coastline. It's a big issue for trying to maintain our coastline with sea level rise because the coastline is also sinking. So we have a sinking coastline added to global sea level rise. It doesn't look good for coastal Louisiana when you've got these two forces both working in the same direction to submerge wetlands. So these faults, and you can see all of these faults in the image accompanying all of this material, you can see that these faults are all sort of east-west oriented, and you very, very often have motion along the faults. Wherever you have motion along the faults, you do generate earthquakes, even if they're fairly low magnitude earthquakes. So that's where we're going to wrap up our talk about earthquakes for now. In the next lecture, we'll talk about how these earthquakes are used in understanding the Earth's interior. Until next time, keep rocking.